Hey, morning everyone. It's Mr. Ferreira. Welcome to my YouTube debut. It's Monday morning. We have a little bit left to do with circular motion before we move over to the second half of this unit, which is looking at gravity and planetary motion and satellites. I just want to basically see how this works out, see how what you think of getting a lesson this way, and seeing if if the video works and if there's some value in it. Okay, so I'm just going to go through one example today. It's a pendulum question. I've written it on the board here. I'm hoping that you can see the board okay. So it says example, the conical pendulum. So this would still be part of the section 5.1 to 5.3 material on circular motion. This will be, like I said, one of the last topics. So again, a conical pendulum. I think all of you should probably have had some experience or exposure to a pendulum. It's one of our physics tools that we use in a variety of ways, but probably only the physical pendulum, the simple pendulum, where you just have a mass on a string. I have my trusty, you'd think being at home I could have different props than my keys from school, but nope, here are my keys from school on my lanyard, and they're going to serve me just fine for this. Okay, so here, imagine this is a mass. Here are my keys. Okay, and then a string, and our simple pendulum is just move it over, let it go, and then off it goes in this periodic motion. Okay, and so the period here would be the time it takes when I let the keys out of my hand and it returns to my hand. One period. Now, the example we're going to do today, it's called the conical pendulum, and that comes from the word cone, because instead of pulling the keys off to the side, I'm actually going to get it to go into a circle, and it's going to sweep out a cone. So I'm going to do this here, and I'm not sure what kind of an effect it's going to have in terms of this video, but the pendulum, hopefully you can see it, the keys are just moving along, okay, but not back and forth like a simple pendulum, but actually sweeping out a cone, as you can hopefully see. So it's moving in uniform circular motion. And as with all the questions we've done, that means, okay, we just run this and we do this as a dynamics problem, Newton's laws. So we're going to analyze the forces. We're going to do a force diagram, analyze the forces, get an expression for F equals ma, like you've done in physics 11 and physics 12. But now it's like, okay, this is a different type of acceleration, so we have those centripetal acceleration formulas that we'll use. Okay, so here we go. So I'll write up the question first, okay? So basically, here we are. So here's our Monday morning example, conical pendulum. So the question is basically, what is the length of a physical pendulum shown below? I keep saying physical pendulum. That's an AP calculus thing. Conical pendulum if the period is 1 second. So here we go. Determine the length of the conical pendulum shown below if the period is 1 second. So I don't know if you are writing notes down or if you care to write notes. If you are, I'll give you a moment. And that I get some students tell me when they come back and visit, they take their Physics 12 notes end up being useful for the next physics course they take. So if you're building yourself kind of a library of notes, you want to add this example, a pretty standard circular motion example. I guess of course the question comes with a diagram. I said shown below, so let me draw a picture of this conical pendulum. So there it is, my pendulum just sweeping out this cone in circular motion. Again, there is a 3D aspect to these problems. So I'm trying to draw 3 dimensions on a board. Okay, so the first thing we do, as with, like I said, all of these problems, okay, you imagine this pendulum is sweeping this cone. And we ask ourselves, well, we start with, what is the free body diagram? That's always going to be our step 1. So if I was to take a snapshot of this pendulum and say, okay, how many forces are acting on the pendulum? Because I need to know that to find the net force. So if you said 2, you're right. If you said 3, you're technically right too, because there's air resistance, but we're going to ignore air resistance. So I'm just going to look at my pendulum and say, okay, it's connected to a rope, so there's tension, and it has mass, so therefore there's weight. So my free body diagram will show me 2 forces. So in my solution, right, I think I have the camera set up so you can pretty much see the bottom of the board, so I can write a little bit more. So there we go. There's my free body diagram. And it's not as useful this way. I'm going to resolve that tension vector. So I'm going to draw the diagram one more time and split up that force vector into vertical and horizontal forces. When I do that, I get a vertical tension component of tension cos theta and a horizontal tension sine theta. Now, as I'm sweeping a cone with this pendulum, the keys are not moving up the chalkboard or down the chalkboard. There is no vertical motion. It's actually just sweeping out a circle. So the motion in the y direction, there's none. The forces must be balanced. And that's going to give us basically this is kind of a standard circular motion problem with angles. We're like, okay, forces are balanced in one direction and the forces are unbalanced in the other. If you could see from the free body diagram here, there's nothing. balancing or canceling out, if you wish, the tension sine theta term. That is a net force, and we're calling that sometimes the centripetal force. And that's how we're going to proceed, is by looking at the forces in the y and the x. We're going to build ourselves a system of equations, and then after that it's just doing math. It's not physics anymore. Okay, so here we go. In the y direction, I'm going to write sum of the forces in the y equals 0, which gives me tension cos theta must balance the weight mg. And I will put a box around that, and I'll just call that equation 1. I wasn't given the mass of the pendulum, and it turns out it will disappear when we get into the math. Now, to deal with the unbalanced force, that's the net force. So here, Newton's second law. Sum of the forces in the x direction equals mass times acceleration. So, this isn't new. Again, this is Unit 2 stuff. Except for we have new acceleration formulas in this unit. Okay? So, and because the question is stated in terms of period of a pendulum, I'm going to use the period formula for acceleration. So this becomes tension sine theta for the net force equals m, and then I'm going to put in 4 pi squared r divided by t squared. And I'll box that. And I think you can see the very far end of the board here. I'll call that equation 2. So, I'll get out of the way. I don't know if you're writing this down, okay? I mean, that's it in terms of physics. We have solved. We have done the physics of this question. But as you know, like most physics questions, to get to our final goal, we have to use some mathematics. And that's where I'm going to go next, is now we'll do a bit of math, and we'll find the length. And it's L, the length of the pendulum isn't even in the question, isn't even in the problem right now. But that's going to come a little later on. I will be able to find the radius of the path of this pendulum. And then with a little bit of trigonometry, we will get the length. The length of the pendulum, if I go back to my original diagram over here, L is right here. That's my unknown. And I will, again, at the end, after I get the radius of the circle that the pendulum is on, I'll be able to relate the radius and the length with a right angle triangle. Okay, so let's do some math, and we'll finish this off. So you can do substitution here, or you can do I'm not. I think you've seen me do it before. I've seen many of you try it. I'm actually going to do this little trick of dividing the equations. So I'm going to take equation 2 and divide it by equation 1. And then I'm back up to the board on this end. So when I do that, I'm going to get tension sine theta divided by tension cos theta, for the left, and then m4 pi squared r over t squared divided by mg. Now that looks a little bit gross on the right hand side, but it cleans up a little bit. Remember, to divide, when we're dividing fractions, we just multiply by the reciprocal. So this turns out to be the same as m4 pi squared r over t squared times 1 over mg. And now you can see, as I said, that mass term disappears. It's on the top and bottom of the fraction. It's gone. And the left-hand side, I have sine theta divided by cos theta. I have tan theta. So I have tan theta equals 4 pi squared r over gt squared. And now, my only unknown in that equation is the radius of the circle. So a little bit of algebra now. I have gt squared tan theta equals 4 pi squared r. Solving for r gives me r equals g t squared tan theta over 4 pi squared. And now I plug some numbers in. So 9.8 for gravity. I don't need this piece. 1 is the period. And then the angle was 25 degrees. And then over 4 pi squared. And then I believe the calculator will crunch out, if I did it correctly, I get 0.116 for the radius. So, I suppose if there's any benefit in doing an example this way is if sometimes I erase every once in a while I'll get a student going, "Oh, you erased the board. I wasn't ready. I wasn't finished copying." Well, you have the option of sliding over that little bar and going back to the video if I did erase this too fast. But I am going to erase this part of the board right now, and then we'll just finish the question and determine the length of that pendulum. So, going back to my picture, that pendulum, okay, I can form a right angle triangle. So there's the length that I want here, the length of my string. Okay, and then this was sweeping a circle, and we've just determined the radius. R of that circle. So I can just use now trigonometry, the sine ratio. Sine of 25 equals R over L, or L sine 25 equals R. So L equals R over sine 25 equals 0.116 meters over sine 25. And I get the length of string required. I get 27 centimeters, so it comes out 0.27 meters, or 27 centimeters. So that's it for my, like I said, YouTube debut. I'm pretty sure I got this figured out. So if you're actually listening to me right now, I will be able to post this onto YouTube and you can have a look at it. And I'm not familiar with actually posting videos on YouTube. I am assuming that you can give me the thumbs up and thumbs down, and there's comments. So if there's something in the example that I did, so I think I can make sure that the comment section is on. I'll read comments and going, yeah, I'm pretty sure you made a mistake in that question over here, Ferreira. Let me know, please. If there was no value at all in doing a question like this, please let me know. Be honest. I'm not. I can take the criticism, and then yeah. So I'm gonna stop this video now, and that's it. I will. Well, we'll see what happens in terms of making more. Okay. Stay safe. See you guys.